Okay, seems like we're streaming. All right, seems good. All right, so let's pick up where we left off. Proving the Schwartz-Zippel Lemma. Now, let's see, where were we? Let's look over here. Right, we had done this sort of like first half. There were like these two critical, so if I go over here, right? Basically these two critical things, right? We have to prove that probability of B is less than D minus I over S, and probability of really A intersect B complement is less than or equal to I over S. And so we have like, set cardinality analogs of those statements here in the proof. Now we have to prove them. And last time we had proved all of this, which was like the first one of those. So now we have to do the second one. Now, how do we prove this? Right, so we have this, we use the like inductive hypothesis back here. I forget where exactly the inductive hypothesis gets used. Maybe it's in the like sort of main proof at the end. Search for finite PHI for age. Right, we use it at like the very beginning. Of the proof for the first half. And so the first half proof is like this stuff. And this is what uses the induction hypothesis. Now we have to prove the second half, which apparently does not use the induction hypothesis. Not totally sure, but I think it does not actually use it. So we just have to like work out how to prove it. So we have the cardinality of this set. It's like function fin set thing. Right, function fin set is this like function that we defined ourselves, which is used like fin type based on fin type pi fin set. You may want to go back at some point and just maybe just like, not actually define this, but, like inline all of this, because there's probably like lemmas about this. Yeah, like mem pi fin set, this is like one of the theorems that I'm going to want to prove. Okay, apparently like there's an error here, which is interesting, but for whatever reason, like I'm not experiencing this error in my main file, so I'm going to ignore the error for now. We'll see what happens. So we have this like, so we take function fin set and we filter out all of it's like this like finite collection of functions from F into this, or from this finite set into F, or really into S, right? The thing that we want to do is like we want to filter out so only those like values which when P is evaluated on them, it returns 0, but when P sub I prime is evaluated on them, it's not equal to 0. And I think that like the big moral of the story is that if we just look at the the latter elements. All right, so this is a function from fin nat suc n, which is, so it's a function from the set of natural numbers from 0 to n. But if you look at just like the numbers from 1 to n, right? And you like fix those. And you say, okay, like make sure that p sub I prime does not evaluate to 0 on those. Right, yeah, so like given that p sub I does not evaluate to 0 on those, and the probability that like the whole thing will evaluate to 0 is less or equal to I over a cardinality of S, because polynomials only can have I roots if they're I degree polynomials. And that's what we sort of have concluded, I guess, is that I is the I is the degree of this polynomial. Or sorry, let me be precise about that statement. I is the degree of p prime, which is p prime is just like an analog of p. It's like a multivariable polynomial that's been cast to a polynomial of multivariable polynomials. And we know that it has some like I is like the largest value. The degrees of p sub I. We know that this whole thing is of degree I. If pi is not equal to 0, is of degree I. Right. Right, so for like a fixed valuation of these r's, right, p, like considering this like single variable polynomial for the value x1, right, this will not be 0, and therefore the degree will be pi is not identically 0. For all j larger than I, pi is identically 0, so it will be 0 for all greater values, and so the degree will in fact be exactly equal to that when we evaluate. Yeah, it makes sense. So that's something I feel like we're going to encounter that later in the proof. Right, so for now, what I think we want to do is this, right? So like all of this has been phrased here in terms of like this cardinality here. So I think what we want to do is we want to like re-express this as a sum, right? A sum over all like valuations, like function fin sets from nats again to fs. Where that is equal to 0 and the other one is not. I feel like we use like some useful tool here to like, basically what this involves is like reasoning that the cardinality of a particular set is equivalent to the cardinality of that set when we map it through some bijection. And I feel like there was some, like what exactly was card product? Card conger, that was what we did. Let's just, I think there's like a, I think I had like the documentation open for that. Yeah, here it is. And so I have some f, which maps alpha to beta. And given a bunch of like properties. Turns out to be like that the cardinalities are equal. So what is the set which I want to prove this equal to? So this is a set of, it's a finite set of functions from fin natsuck n to f. And what I sort of want to prove it equivalent to, again, actually, is a finite set of functions, like a set of elements of type like f cross fin n maps to f. Like we did something very similar here, right? Right. So like, what was the function here? Like we had a function ab from this. The function that like ab maps to make fin suck function, which is another like random function I defined. So I think we might like apply. Of course, this is an equality, so maybe we should just use a rewrite. Let's use our brains here. Can we do rewrite this? What happens? Type is not of the form. AB has type that. It's the issue that right, so F maps from A, or F maps from alpha to beta is the problem that we've got like the symmetry order wrong, because like we definitely invoked like symmetry. Apply EQ sim here. So maybe what we want to actually do is like the reverse of this rewrite. Still complaining. Invalid field notation. AB, I don't know what the type is. So like maybe if I like declare the type of AB, maybe it should have type F times fin and to F. Okay, so it's no longer complaining. There's a there's like a meta variable here, which has to do with this like set. S is a fin set of alpha. Right. So the thing is we need to be like precise about like what actually is the set of right. So like before we apply this rewrite, we have this like set from fin suck n to F. And we need to be talking about like what is this like filter, right? Like what does this fin set filter look like when we like when we map it through that bijection? It really is a bijection, right? Is there like, because like what I'm thinking is that like there's a bijection between mat suck n or like fin suck n to F and F times fin n to F. And it feels like because there's this bijection between the types, it should be like much simpler to do. Like there should be like a simpler theorem. Like it shouldn't be as complicated as this. It should just be something like let F be an equivalence between alpha and beta. Then finset.card S equals finset.card like image of S under F. Like like look up what an image is. Like, what is this? This is MathLife 3 documentation. What I want is like finset.card image or something. Well, there's card image 2. There's card image of injective. Well, bijections are also injective. Yeah, like what's the difference between map and image? It's like something to do. Like finset.map has to be an embedding, whereas finset.image is just the forward image and it can collapse. This is an embedding. I think right, we decided it was like equiv python suck last time. Like this was the equivalence that I was using. Is there a way of getting the embedding from the equivalence? Equiv dot python suck. There must be, right? Like the point is that this is like some equivalence, right? It's like an equivalence. It's this equiv structure. And I can get the function from it, and I can get the inverse function from it. But can I get like the embedding from it? Like equiv.toEmbedding. Yes. Okay, so this is what I want. I'm suddenly wondering if all the work that we did last time was like totally could have been simplified massively. Like finset.card conquer. Like instead of applying this, what am I like saying here? I'm saying that instead of finset.card conquer, we could do finset.card map. I can convert it into finset.card map or something. What is convert? Convert is, yeah. Okay, this is maybe me going on like something of a tangent, but let's like, which one is more complicated? The equivalence. Sorry, what's the equivalence? Can I like duplicate this? Go back. Python suck. So which order is it in? Right. So this was the order actually. What I want to know is like, okay, let me just start writing it. Can I prove this via convert inset dot card map? Applied to the equivalence, which is given by equiv to embedding applied to the equivalence equiv hyphen suck where I have to provide n and beta equiv hyphen suck. What were the arguments that I gave that before? I think it's just n and f. Just to like visually separate that. See, I bet there's like some like map filter. So that failed, right? Yeah, okay. It's a little bit like too optimistic to think that it could have proved all of that, but only seems quite possible. Just want to like to note that this is like a new way of potential different way of proving this. Is there such a thing as like inset.filter map? Inset map, is it map filter? Map filter? Inset map. Okay, that's actually totally fascinating because I was not expecting this to like reference equiv.to embedding. Oh my god, is this like some genius of the library that I was totally unaware of? It actually has, okay, well, let's just rewrite, yeah, just a whole bunch of implicit arguments. So let's just rewrite that. Rewrite inset dot map filter. Let's put like a dot here. So that rewrites that. The point is that this is just like an alternate way of proving it. It's potentially like a golf. It's a dot filter. So I think we still like have to maintain all of the like interactions. Like we still have to prove that like some things about like, okay, what is the action of finset dot filter on this function finset thing? What like how does like equiv to embedding interact with this? Comments if I like try to simp. Just simplification. Again, like this kept happening last time. It kept like doing all these polynomial things that I didn't want to happen. But there are some interesting things that have happened. This is proving inequality, right? Inside dot filter. See, like this is where I think I would have to like apply extensionality and like break it down. Just leave it note to myself. Okay, so let's like return to thinking about what we're trying to do here. I think it's something very similar. Maybe we want to like use this approach. So let's do this. Instead of like card conger, let's try this one. Oh wait, are we trying to prove something is less than something else? Oh, okay. Yes, yes. All right. Okay, maybe instead of card map, this is like an equality. So maybe instead of this, we should be rewriting. Maybe we should be rewriting backwards because I think that forwards direction. Right, so this is now the cardinality of a map. That's a cardinality of a like f times fin and f. So this is where okay, it seems to me that there should be some lemma that says that if I am looking at the cardinality of some finite subset of a product type, that should be equal to the sum over one of the types of the like projection of the sum of the other type, right? Of the slice, right? The slice of that set. So like, not exactly sure what that lemma is going to be called. Finset sum product. That's some product. Right, okay, so clearly the sum of a Cartesian product should just be the sum I feel like I saw other things. Since that's some product, right. Since that's some. What I don't want is this Cartesian finite set product. What I want is just like something where it's like a product over some like finite set which is a product type. That's some fin set product. What is this? Okay, here we go. This looks promising. Obviously this is prod, but we want the sum. Some fin set product. R is a fin set of gamma prod alpha. Yeah, too many like products, like product has too many meanings. R is a fin set of this product type. And the point is that the sum of like the fin set sum, right? So okay, like start off, what is the type of fin set sum, right? It takes in a finite set and actually a function, and it can be just the sum for x and s of the function, right? So we have some function, fun PFP. This is a really strange way to okay, like this is also a little confusing to me because I don't know how it binds. I assume it binds in the natural way, but I also don't understand why this is not just F. Because I believe that this is meant to be like a single function, right? Maybe I can okay, yeah, it's like a two additive. This is not going to help me that much. I think like let me just try like doing this. I think I'm like still a little confused. This is not because I have a cardinality, right? What I want to say is that like the cardinality of this product of this like fin set of products takes the form of a sum. This is like not exactly what I want. Because nowhere here does it mention cardinality. Okay, let me try searching for it again. Still seems like useful somehow. Let's see if there's I was like, inset card prod. Yeah, well, this is obvious, but this is not what I'm looking for. Maybe it's just time to write the lemma that I need. And we can work out later what the MATLAB form is, right? But the lemma that I need is lemma set dot card of a product. I don't know how to card product something. The point is that if alpha, beta are types, and R is a fin set of alpha, fin set times beta, then it is the case that, do I need to import, how do I sum, right? The sum, no, this is not what I want. Okay, fin set dot card R, right? This is an extremely general theorem. It applies to any cardinality of this type, of a fin set of elements of a product type. The cardinality of R is actually going to be equal to, and this is there should be a left here or something, either left or right. The cardinality of R is equal to the sum. Oh, I see. I'm about to get maybe this is why I'm about to be told that I don't know that alpha or beta are finite types. That's annoying. Maybe this is why this happened here. The thing that I want to say is that this, if I take the sum over all alpha, yeah, but it's not going to work. It's not going to work because it's going to need fin type A or something. Fin type alpha. Sum over A and alpha. Maybe it has to be in alpha. Of what? Of the cardinality of R dot filter R dot first equals A. Sorry. Okay, so what is it complaining about? Expected token. Expected token. I worry that I need to import this or something. Shoot. I have forked my setup. Okay, because I tried importing something and realized that none of the other. Okay, can I yeah, I need to do something like locale big operators, but I mine. I feel like I watched something that said it's not. That's not how you do that in Lane 4 anymore. Okay, let's try restarting the server. Main server printed an error. Got shutdown request. Okay. Maybe I can restart the file. Gonna try again. Let's see what it says. Yeah, not happy. Okay. What is that? Have I really changed anything? I feel like I haven't actually changed anything in this branch. It's really weird that all these other files are failing and stuff. Maybe I should have done get exclamation point there. No files to download. Okay. Decompress things. I wonder if this is provable from this theorem. Okay. Did I run that? Now I'm gonna restart the file. Okay, now it works fine. That's interesting. All right, cool. I'm gonna take a quick break. Okay. Yeah, I don't know why my mic always seems to turn off when I take the headphones off. I need to reset them always. Okay. So our system is working again. You need to be approving this. The issue is that like the type isn't even necessarily finite. Right, like this is not going to work for us because neither like f is not even necessarily a finite field. It's just this like one subset of it that. Okay, maybe like the key is that we need to invoke this theorem. We need to get it in like a place where we can invoke this theorem. So we need to like, oh yeah. So maybe what we need to do is actually like reformulate like finset.card is equal to like the sum over a and r of 1, right? Maybe that's what we need to do. Surely there's a lemma like that, like finset card sum. Card equals a sum of ones. Yeah. Like a card is a sum of ones. And then like finset of r is equal to finset of s function c of a sum of this. And it's going to be a sum of ones. And then I can like undo. Yeah, let's try that. So remove that. I mean, like it's interesting because like we're basically going to try and prove a theorem that's a little bit similar to this. Maybe it should be like extracted as a lemma. But I won't worry about that now, I guess. So a card is a sum of ones, so rewrite finset.card sum ones. That was successful. And now what I want to do is I want to apply my finset.sum finset product. Let me like read this carefully. H. H is the condition that for all P in gamma cross A, P is in R if and only if P first is in S and P second is in T. No, wait. If P is in R if and only if P first is in S and P second is in T of P first. Right. What is the primed version? Some finset product prime and some finset product. What is the difference between these? In this one, f is a function from gamma to alpha to beta, and in this, f is a function from gamma times alpha to beta. Okay, so it's like very similar indeed. That's okay. I think we want the first one. Yeah. So, some finset product. What happens if we just rewrite? The thing is that we can rewrite it, but we're not going to get, it's not going to be obvious. What's going on? Like the whole point is that this, like the thing inside the sum, let me go inside dot sum of this whole map thing. The point is that this map, let me just think about this for a second. Sum fin set product. P is in R if and only if P first is in S and P second is in TP first. So it has to be like exactly equivalent. So I feel like I might need to be working out exactly what S and T are right now. I'm just like a little bit nervous that there's like a cardinality version of this with these lemmas that would be easier. I don't really see it. Okay, so if I'm going to apply finset.sum finset product, I need to like choose the S and T that I'm going to be using. Like just to recall like what this expression is, right? It's the filter like fun R equals 0. Finsuck is not equal to 0. Function finset where they're all in S. I mean, one thing is that because it seems like this whole logic like chooses the value of the second chooses the value of the after this, right? It feels like it chooses the value of the fin n to f first. So it feels like that should be the first, like for this one, it actually feels like that should be the first, it should be first in the pairing. Instead of f times fin n to f, it feels like we actually need to permute those. Unless there's some sort of like thing where I can do left. Like, so is there a version of some finset product where I can do the left one? Right. To the right one first. Yeah, sorry. I was saying left, but I guess I meant right. Is this it? Alpha and gamma. Sum over S, which is the finset of gammas. Yeah, so this is what I want. Finset sum finset product right. Okay. Let's just copy that out here. Of course, it's going to complain to me that I didn't tell it what F, S, and T and stuff are. Or I guess it's not going to complain, but it's going to like force me to like choose S and T, and it's going to be like, oh, these meta variables, what are they? Yeah. And so, right, so returning here. We're returning actually to the very beginning before I like, right, it's the like the values of the successor such that P sub I prime is not equal to 0. Yeah, so what is S? Okay, so like, first of all, we have no trouble inferring R, right? We shouldn't have any trouble inferring R because it's on the left-hand side. Yeah. The only thing, so we can put one of those there. And then the question is, what is S? So question, what is S? And like, apparently you can do like this, and then you can. So S, is there a way? Yeah, okay, it's interesting. It tells me that the placeholder I'm looking for is this. It's a fin set of fin ends to F. And which fin set is it? It should be the fin set that satisfies this. So I'm actually gonna like copy this out, right? So what is S? S is going to be, right, so like, first of all, this all gets scrapped. And I think it's not, like, we don't need the composing with finsec because it's just going to be this. And this is not going to be nat.suck. It's just going to be the straight that. Ooh, invalid coercion notation. Why is it invalid coercion? Okay, maybe I just need to like not tell it that it's coercion and it'll figure something out. Okay, cool. That seemed to be successful. Now we don't have like this meta variable S. We do still have the meta variable R, or sorry, the meta variable T. Yeah, RST, naming of things, whatever. So let's try and figure out what that is. R. Now the type, I literally keep changing the letters in my mind. Okay. Yeah, it needs to have this type, fin n to f into fin set of f. And the point is that it is going to be okay, so it's going to be, right, so it's going to be, I guess I'll just say like fun R to something, right? Right, no R's of that type. It's sort of annoying that it doesn't like show the goal state over here. Like when I have this, like I'm looking for fin set of f. So what exactly am I looking for now? Like to return up here. Like return again, right? This time it is going to be finset.filter. What just happened? What did I press? This is insane. Like I pressed some key. I don't know what key I pressed, but it took me to the thing. This is something that I was like trying to figure out how to do. This is so annoying. I don't even know what key I pressed. Okay. Like I pressed some key and it took me to the definition. What did I press? I pressed like control something. Okay. Okay, so let me just try and write it out. Finset.filter. Oops, to something. We're filtering over S, not function finset something S. And so what I have to do here, I have to use the fact that R is, it's stuck. Oh, there's a decidable pred? Wait, who is demanding that I have a decidable pred? Filter is. Okay, well, what I want, I think is, so we got the not equal to 0, but now we need the equal to 0. Fun F. The thing is, it's got to be like the gluing of F to R. So this is like if I put this in, it's gonna like complain at me that it's not the right type. Yeah, like P has type this, but it's expected to have type this. So I need to like glue R to P to get R is of fin N to F, F is of F, and what I need is like equiv by finsuck, the inverse function. I need like the inverse function. Okay, let's just go. It's going to be this dot in the fun of, we have to do F comma R. Or maybe it has to be, okay. Yeah, okay, it seems like it has the right tuple notation. Yeah, it's interesting. Like it used to be that you had to write like wide angle brackets, but now I guess you don't. I should like consider checking if I can like undo that here. Okay, so now I've done a big rewrite. What has happened? I rewrote this. And so basically, so now I'm left with two goals. What are these two goals? The two goals are like, okay, I did a rewrite, so I still have my main goal, but also in some finset product right, there's this like H, right? So I rewrote, but I didn't like prove H, and so H has now been like spalled off. Okay, that's manageable. Okay. Yeah, it looks like H is second. Let's sorry. Question is, which should we prove first? Yeah, this is where it would be like nice to just call ASOP and have it work, but it's sort of tricky for that. Because it's not easy for it to like, there's going to be like something that it gets stuck on is the thing. Yeah, how to like deterministic timeout. Okay, cool. At least I thought for a long time, you know? Uh, can I do this? Can I like, will it figure out the product? Unknown tactic. Wait, is it just intros now? Seems to be. Wait. Expected command. All right. Do I have to do it this way? Wait, like how do I, I want to introduce f times fin, and this is super dumb, right? I have like, okay, like I can call it like p1 if you want, and then I can do like our cases p_1 with like f comma r. Does this work? Yeah, so how do I do this in one tactic? I feel like there used to be a way of doing that. Whatever. I feel like, yeah, I feel like there's a way to like get the like this to simplify. I feel like it's unfold like projes, but I think it's like unfold projes. But I don't know if it's implemented. Yeah, it says unknown tactic. Let me just make sure that like I'm not insane and it is a MATLAB 3 tactic. MATLAB 3 docs. Now this is the MATLAB 3 docs tactics. Unfold projes. All structure projections, right? That seems right. It seems like it would do what I'm trying to do here. To do, right? Unfold projes tactic in mean for. Sort of interesting. I wonder if it's like the sort of tactic that doesn't ever like appear in MATLAB itself, because it's one of those things which is only for like visual. Does like all the proofs actually just like work because it's a definitional equality or something? So you can actually, like, after you've written your entire proof, you can just delete every case of unfold projes because it's actually doesn't like affect the underlying thing. It just sort of affects how it appears in the. Anyway. So we have a bunch of things here that we should like get to proving, I guess. You have to prove an if and only if relation. Seems reasonable. I guess let's get to it. Constructor. I wish there was like, okay, I wish there was a case that would at least like unfold all the like sort of logical things in it. Like, is there something like that that will like, just apply constructor and, intro as many times as is needed and just like give me a big list of goals to prove? Sorry. So now we have this big thing here. again, it feels like um, there's some way of doing this much more efficiently than I'm doing it. But I just like, feels like there should be some way of like defining this sort of like equivalence and having it all work out. Yeah, but it's pretty tricky. Right. Intro H of R. Then we want constructor again. I decided there was like some map filter, right? Did I ever apply that? Where was that map filter? I'm not sure if it's, the problem is I don't know if I'm making progress or not making progress, undoing progress when I like call this lemma. Like I think everything is solved goals, right? Sorry. This maybe? I'm confused. No goals to be solved? Do I need to like do this or what? I don't get what happened. I have one goal. I apply constructor. I need like two constructors here, right? Okay, now it's not complaining at me. Okay, so did map filter like improve anything? Function finset. Yeah, it's just like a big big like algebra of like filters bash. Like before I even intro, I'm tempted to like simplify because it'll be like simplifying with mem filters, right? I have like a bunch of like mem filters here. See. Well, let's just see what simp does. I mean, of course, it's going to do all those weird polynomial things that I don't want it to do. Like I can make a note of that. Like all of these polynomial lemmas. Just like going to quickly make a note, like note are triggering, but I don't want them. You can like investigate whether that's appropriate. Also fin cons. Like what is this cons and like what is causing it to like pi fin soxim. Fin dot cons. It's very close. What is fin dot cons? I get the like sense that fin dot cons is like what I should have written here instead of this. And like instead of this, it should just be fin dot cons of these two things. What is fin dot cons? I know I like was shown it before. Like I somehow found it before. No, I need, okay. Sorry, this can go. Get the tab and fin dot cons. So, adding an element at the beginning of an n tuple. Okay, wait. This is just, okay, what is going on? P is a function. It's all dependent, which makes it a little bit more confusing, but it's okay. So x, like just forget a moment that like that alpha like has this variable and just treat it as alpha, right? So it's a function from fin n to alpha. Okay, it takes an element of alpha and a function from fin n to alpha and returns a fin and returns essentially a function from fin n plus 1 to alpha. So it is essentially what I want, right? Even if I haven't been writing it this way. And there's all these very nice lemmas that I'm sure will be very helpful. All these like nice simp lemmas. So maybe I should just like note T. Okay. I'll just like copy. It's the stuff inside this, like the pink parentheses here. Note that this can be more simply written with fin.cons. And this is where I feel like so close. If I just wasn't using like function finset, I feel like the simplifier might figure out what was going on. Like fin.cons pi or something. Because yeah, like what's the real name? The real name. Okay, what's the fake name? The like function finset right? It's really named pi fin set. Function fin set is really named pi fin set. Fin conv. Yeah, I'm so close. Like fin.cons pi fin set. It's not there, but it's like so close. Like let me like write out the lemma I want, right? The lemma that I want is that if I have fin cons, and in fact, like the fact that it's dependent makes it even like more just like genius because pi fin set is dependent as well. So what I want is some lemma. Oh, okay. And I've written it like again here too, right? This is just fin.cons, right? Like this function is fin.cons, right? It takes in dependently an n. Okay, it's like a dependent version of it, but like forgetting that. Yeah, we're so close. Let me just read this. Make fin's function that I've written here is fin.cons, right, of n, a, b, and k. I think that like corresponds to x, p, and I. I'm learning so much about the like fin API. There's also like snock, which I bet you is like the same thing. Yeah, I feel like this is like the big brain move is to make like one simplemma involving fin cons and fin type.py fin set, and like the whole thing will automatically prove or something. Okay, let's maybe the first thing to do. Okay, so like to what extent do I actually use this? Like make fin function. Like so I use it here, 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 compose with suck. Yeah, I bet that's another thing that would be. This is just like fin cons suck, right? Yeah, it's like fin cons suck. And I rewrote a bunch of things here, but it's like so close to being true. Okay, so the key, so like yes, the refactor, easiest way to refactor is probably just to like replace the definition first and then like go for it later. So I think that instead of this definition, what I want is it's equal to fin.cons of n is implicit, x should be b, p should be a, and I should be k. It's still complaining at me. Why is it complaining? Oh, fin n plus 1. Wait, what? Has type, but is expected to have type f. Yeah, the point is that like alpha I is always supposed to be f. Adding an element at the beginning of an n tuple to get an n plus 1 tuple. Fin cons. has type something of k, which I did not specify. Does it work if I do like fun, whatever it is, please return F? Okay, glorious. It seems that that has worked out. Okay, and now a lot of stuff has broken. Because I unfolded it here. Make prod of Braj. Yeah, this was like this, this is just what I wrote. Yeah, this is like something that I don't like. It must be in the library somewhere, but I don't know how to write it. Oops. Okay. So after I do this, it says that, can I I want to do simp at h make equals. Simp question mark at h make equals. And maybe it'll realize that, yeah. And now all I should have to do is this is weird, text. Is it and dot left? It's just the left-hand side of h make equals. This is so annoying. Maybe I just need to be doing obviously I did this at some point. Maybe it's, okay, maybe it's undo copy. This. Yeah, okay, it's happening now. Is it is this the exact same thing as, ugh, this the same thing as this? I don't have to do these rewrites. It's okay, what is the message? What am I rewriting? Tell me. Try this. Simp only and cons equals cons at h makes. I unfold this, if I do this, I don't know what's going on. Cons of this dot second. What is this? What is this size? Cons of this dot first and like thin dot cons of something dot first and something dot second. Can I just like simplify maybe? Maybe it like knows enough about like what fin dot cons is to tactic replacement this. Define as core supply. Fin dot cons. See, I feel like this has got to be like a theorem. Is it not exactly fin.cons suck? Fin.cons v0 and fun j b to fin suck j of x. No, phonics seems to make sense. Right, this is just like b as an arbitrary function. I don't think I need to use hb, right? This should just be true. By cons b0 and b cons self-tail. Feels like I'm so close, but it's somehow not proving it. Like something is like broken in the API. It feels like Simplify should just get it, you know? It doesn't manage to succeed. Fun j to b. Like, what is tail? Fin.tail. It's q fin suck j. Yeah, so close. It's like is I feel like I literally just have to do, what is it, like convert fin.consult. Or maybe like exact. Wait, what are the things that are slightly weaker than convert? Convert, like refine. I want refine. Fine with, I don't know what the Q is, but yeah, I guess it's B, right? Can I just refine? Maybe if I don't functionally extensionify, I can refine. Okay, and after I refine, what happens? Oh, is this really the issue? The difference between nat.suck and n+1? Ooh, this is one of those like type things. Is the XB? I don't get it. No goals to be solved. Okay, I'm confused. Is this just? Are you fine? Okay. The below is a simple lemma. Why does the above simp not close? Okay, so we're in the middle of this refactor. Make fin suck function. I basically want to like totally remove make fin suck function. And the first thing we have done is to redefine make fin suck function as this thing. It's like, why can't I? It's very annoying to me that I can't define it this way. It's like you cannot infer fincons, right? I have fincons here, but it is not capable of inferring like what alpha is, right? It's just this constant like dependent function, right? Not, I don't know, like when you have a dependent function, but it's constant. I don't know what you're supposed to call that, but it's like this. It seems that all of this is written in a very dependent way, and it's okay. Wait, why is it complaining? Wasn't this fine before? I'm a bit mystified. F as type sort. What did I do? Ah, okay, there we go. I needed the at. Hmm. So the question is, should I just like what I feel like I want to do is just like replace my call to make fin.dot function with just the cons and see if I can like get away with that. Right. Basically, the point is that it's equivalent to this, right? Any complaints? What? Fin.cons f bb.second has type this. Oh, I need to permute things. It's like this, but also the arguments are permuted. And so there was like one more like theorem, right, which is make make this, which I hadn't proved. Now I want to like, instead of like fin.cons, well, this is just fin.cons suck, right? So now that function, now that lemma is proved. Was that the like? Okay, there's multiple lemmas here. Was I proving the wrong one though? Like if I go back down, yeah. So the critical one is make fin suck function mem function fin set. It's this one. What I want to replace this one with is fin cons. Mem function fin set if and so basically the thing I'm going to do is switch the B and the A. It's a member of this if and only this is true. And so the point is now I'm going to go back down here and replace that. And now it's going to come over here. And make fin suck function comp suck is going to be replaced with fin.cons comp suck. Okay, one more. This is just like an unfold. There's nothing to unfold. And so now it's fine. The only errors are later. We can delete this. Okay. Only thing left is like unfold. Okay, so obviously there's no, this again can be, this also can be deleted. You can like remove all references to this like dumb function that we made. Now that we have found what the name of the function actually is. We can delete this. Delete this as well. And finally, we can like just delete it off the map. Yeah. And now the only thing really remaining is this. It's like, can I also delete function finset off the map? Because like this is fin.cons with some like dependent type here, but like function finset also has this dependent type. Okay, I'm gonna take another quick break. Okay. Yeah, so next order of business, completely remove references to function underscore finset. And replace them with pi finset. Okay, like, so first I guess let me delete all of these like random things. Is this, what is this? Is this used at all? Fine. No, it is not. Finset. Yeah, this is used like 26 times. I wonder if I can remove it. Like, this isn't, like, look at it more clearly. PyFinset takes in like a type map, returns a fin set of maps. Yeah. So can I just like do this? Right, I'm like consistently doing function finset underscore underscore s, which suggests that like the A and the B could have been implicit. Make a definition. I guess like where are the other function finset things? Hyphen set f. See, this feels like a SIP lemma to me, but mem python set. Python set. This also feels like a subset. We'll see if like I get contradicted later. So instead of function finset, what I want to use here is python set. Okay, let me just like think about this a little bit. I have function finset defined up here. Like everything is fine. What do I get here? The issue is that it can't rewrite because it doesn't know. Cons mem python set f. Now it doesn't know because did not find like python set. Now, so like I think the solution to this is we like unfold function finset. Unflawed, unfold. Here we have mem function finset, which we want to replace with mem python set. Mem python set. Okay, and now what do we have? We are now trying to prove some kind of goal here. Okay, says HB with HB and HB prime. So constructor, wait, so when I apply constructor, I have HB, I have B, member of function finset. Something has gone a little bit wrong here. Right. Equiv defun, equiv by fin second FB. So delta Cartesian product. I think, okay, I replaced this. Do I need, is it that I need to like, do I just need to like unfold function finset a little bit more? Unfold function finset. What happens if I do this? Yeah. And now the whole thing is happy. Yes. Yes. Wonderful. Okay. And so like the point now is that like instead of a whole bunch of function finsets, I should just I should probably get rid of function finset entirely. But rather than do that right now, instead, what I think I'm going to do is I'm going to approach this one, like function finset is used here. Right, so I'm now trying to prove this other one, and I'm just going to do like a quick unfold function finset here too, so that everything is in terms of like things that are in the library. Okay, well, except that I have like put that in there, and so I'm going to like unfold function finset here too. I also am going to try and unfold function finset here right before I ever do anything. And now, right, I want to like see what happens. Okay, I simp only, like let's like return to making this like a simp question mark. And the polynomial stuff will happen, but mem pi finset. Okay, this is like promising. Don't know. Okay, lots of like, yeah, let's delete the polynomial stuff again. Okay, well, shut that down. And now what do you look like? Comp apply. This is interesting. This is like a simp lemma. Wait a minute. I'm a little mystified as to why this didn't trigger up here. Okay. Go to definition. What? Yeah, that is weird. Just another thing to like try and figure out. Wait, okay, is the whole like, I guess there's nothing to apply it to, is the problem? Function.com. And now it simplifies. Yeah, I see. The problem is like, how do I make apply work? And the answer is that like you like extensionalify. But it's sort of weird. Because like I would like something that would like literally just solve it. Like what happens like ASOP should solve this. ASOP. Yeah, try this exact REFL. Wait. I'm confused. ASOP solves it? What does ASOP say to do? Apply equals dot REFL. Yeah, weird. So this is, yeah. I mean, so yeah, like what this is telling me is that like this function actually is just like somehow definitionally equal to fin.consuck. Or like the fact of the definition of fin.consuck makes this like definitionally equal somehow. Okay, that's fine. Scrolling back down. So like, what do we get here? We have like a bunch of polynomial evaluations. Very nice. We did two intros, A, B. Or is it BA? Wait a minute. I guess it doesn't matter. We'll do intros A, B. Intros A, B. And so what do we have now? We have like a bunch of like, constructor work to do. Yeah, I'm worried that I'm like not using the right variables for the right variable names, but I guess it's okay. What am I supposed to do now? Right. So two things are equivalent. This statement and this statement. Any eq. Okay, like maybe I don't want that actually. This is the thing that unfolds not equals to an e of to equals of not or something. Not equal to 0. Right. Struggling to see if there's any like other way to simplify this, but I guess there's not. Okay, so when I do constructor, I do intro HFR, you get a big like conjunction of like 3 different things. Like that's where I do like cases HFR with HFR1, HFR2, HFR3. What is this? Just a bunch of things. It has some issue with me. Unknown tactic. What? Unknown tactic. Does it have to be like this? Think about it again. Expected bar. Does it have to be like our cases? Yeah, I fixed it. Yeah, like, this is making me sort of think that like cases and R cases, like, why is there more than one of these tactics? Why not just have like this sort of general nice tactic so you don't like mess up? Oh well. And I think the point is I can also do HFR3 here. Like get more stuff out of it. And now I have to like apply the constructor some more times. Like, so like after I apply the constructor here, it's like I do like intros. No, I have to go even farther, sorry. Fin cons A, B, A1 is in S. Right, okay. I think that like the point is just to like not pay attention to what's going on and just like mechanistically like move forward. I do constructor again. I narrow to the first goal. I intro N. They've gone to the point where it's taking a while to load. BN in S. It seems to me like this has something to do with HFR1. So like cons, fin.cons. What is S? S is a fin set of Fs. Right. Yeah. Right. The point is, yeah, the point is that we can decompose HFR1 further. So fin N. So like apply HFR1. With something. The point is that like refine HFR1, like refine HFR1. The point is that like the conclusion. Like fin, the point I think is that it's like fin dot suck of N. Okay, there's something annoying. There's like this there's this like N, yeah, intro N prime. That's interesting. Like if I introduce a variable with the same name, it gets mad at me. Okay, but like the issue is that like how do I prove that B of n prime is equal to like fin.cons AB? Ooh, A1. What is A1? A1 is the thing of my choice. B is this functional thing. Is there any way to tell ASOP, like, please just use like HFR1 and all of the things that depend on it? See, I know I'm not using it right. A sequence of tactics in brackets, or a delimiter-free indexed sequence or indented sequence of tactics. No. Like, there's something like, I know, I know exactly, I know that it's extremely simple, and I know, yeah, fin.cons. Maybe there's like some way of like fin.cons. The thing is, I want to like decompose. I don't get why this is like so confusing. It's like it needs a fin n plus 1. No goals. Okay, so did I finish it? I think I did finish it, but why does it tell me I haven't finished it when I click here? Okay, obviously, yeah. Obviously, like I have my cursor here, and the goal is actually done. Okay, at the very top it says no goals, but it has this whole thing with expected type. Okay, I don't know what I'm supposed to think there. Regardless, let's move forward. What do we have to prove here? Just like mindlessly moving ever forward. Is this exactly the thing that here? HFR3? Exact HFR3. Okay, it really is starting to get annoying how long it takes. In Patrick Metzow's video, he said I could like type save here and it would be much faster. Okay, that does actually feel a bit faster. That's cool. Okay, sweet. Moving ever onward. What do I have to do here? I have to use constructor for SDS. And I think here it's going to be A and S. And what I have to do is like refine HFR10. And this is exact. This is exactly the assumption. Cool. All right, just chugging right along. We still have this sorry up here, so we have like even after we finish all these sorries, we're still going to have a little bit more to do. What am I doing here? Now it's like, again, a case where I have to intro something probably, right? Yeah. Let's just like, I don't know what F and R stand for, unfortunately, so. For all A, B, A, and S. And so this is like cases, HAB. Let's do this. It's just a very similar thing, cases, HAB. And I bet I'm going to have to do constructor. Let's see how that goes. For all A1, yeah, so intro prime. I guess I should call it N prime, right? So the point is that, like, the point is that this is I want to do casework on N prime. Like from N prime, yeah, the thing is, yeah, so like N prime is of type fin N+1, and either it's 0 or it's a successor. And either way, I'm going to be able to do something. It's actually interesting. This is a conjunction, so I actually needed to go a little bit harder here. A little bit harder with the decomposition. Right, so I have HAB1. So the point is that like this follows from HAB1 and HAB2. Cons some property The thing is I need to like elim N prime somehow. Fin.elim. What are the fin, like elim suck, right? Or like suck elim? Oh, I know there was something. Fin, suck, fin elim 0. Feels like it should be called fin elim suck, right? Fin elim suck. Yeah, I don't know what's going on. Fin of nat. A is a nat. Oh, this is like modulus or something. Interesting. Okay, none of this is telling me what I want to know. Cons. Cons cases. Potentially. What is X? I'm confused. X is used as a variable here. What do I want? Cons cases. Some property of X. It's a property of like a fin n plus 1. I feel like it's probably going to be somewhere down here. Fin 0 elim. What is fin 0 elim? An elimination principle for the empty set. Yes, but where is it for the... Okay, there's got to be something else. With a lim in the name. This is taking me way too long to find. Where is it? Elim. Can I search this for elim? Elim. Fin 0 elim. Is it any of these? Fin.cases? Yeah. It's fin.cases. It just like... Why is it not called, like... Why is elim not in the name? Fin.cases... I don't know, but I know this is n prime. Failed to elaborate a limiter. Expected type is not available. What else do I need? Ugh. I know it's taking way too long to find this. I know that this is like some incredibly simple thing. Fin cases. It's just for who cares? Sorry, I don't know what's going on. Move on to the next one. It's like it really, should be super simple, but for whatever reason, it's not. This is constructor, and we already have, so this is like exec should in theory find it. I feel like library search would find library lemmas and apply your try this exact yes. Yeah, fine by me. Okay. Is that it? Sorry, no goals to be solved. Okay. So that deals with that. And now we have this, sorry. But it's just like really annoying that like this is happening. Like, I wonder if I like don't intro, like what if I do suggest? It's like apply question mark, right? Apply question mark. Yeah, it's never obvious whether the fastest thing is apply question mark or searching through the things. Refine. Okay, it's talking a lot about fin set, which is not optimistic. Like, what is what here? Like the thing is, I feel like I only need HAB1, HAB2, and HAB3, and like N prime. Like there should be like clear. Let me just like try and like isolate how easy this is supposed to be using clear. I can clear HAB3. Is there some way of like clearing everything except something? I feel like there's something for that. Can I delete this? Okay, clear. Removes the given hypothesis or fails if there are remaining references to hypothesis. Okay, whatever. I can clear this HAB1 prime. H, H1, H0. All references to I as well. P sub I prime. I think I need S, but I don't think I need HP, right? I don't think I need like P prime or HP or P. Yeah, like this is where I'm at. I'm like really, really close. Like this. There should be, like, feels like there should be, I mean, maybe not necessarily, but it feels like this should be like, okay, that's weird. It didn't, did it change anything or what? Simp only. Does this solve it? No goals. I don't understand. For race not equals self. No. Just a bunch of like stuff with fin sets. Yeah, very spooky. Not clear to me, like 61. Okay, what's telling me? Okay, what is this? 61, 2. What? 61. Where's 61? Exact. Ruffle. Don't want to have to look at that. Okay, cool. Can resume thinking about this. The point is that this follows from just A, B, HEB1, HEB2, M prime. And really, it could be any, like, it could be any predicate, right? It doesn't have to be like membership in some fin set. It could be any predicate. Thing is, I'm like, I feel like it exists somewhere. This is just one of those really super frustrating things where I like spend however many minutes I've spent like thinking about it, and I'm just gonna like write a new lemma now, and then like when I get to the maintainers, they're gonna be like, oh, why didn't you use this lemma? So okay, let me look again at the lemma I want. What is it called? Where am I? Right. I have like all of this. Let's just copy that. Come up here. Lemma. Like fin.elimsoc. Type. Okay, so like f, the existence of f is not even needed. N is needed. You don't even have to have f. S should, rather than a fin set of s, f should just be like, s is some like f. Okay, sorry, I mean, okay, f is a type. That is a field or decidable equal, we don't care. This, colon, tab, this equals, sorry. Failed to synthesize, okay, and I don't even care about s being fin set f, I want it to be like f to prop. And so now I will do s of BA. I will do s of A. I will do s of this whole thing. Um, what was it? What am I doing here? Fin.cons is supposed to give what is the point? What is going on here? Are you telling me that fin.cons, right? This should be, f. It should be an element of f. I expect it to have type f, but it has type something, which is not that. Okay. You are definitely a function which returns f. A cons, fin cons. Argument A has type f, but is expected to have type what? N is n. This is this. X, right? This should be type X. 1, 2. What's going on here? This should be like n, right? This should be n. F is this type, right? Type mismatch. F has type 1, but is expected to have type what? What is even going on here? It's just a simple type. Who cares? This is annoying. Argument A has type this, but it's expected to have type that. Fin n plus something. I don't really get it. F has type. Why is it expected to have this type? It's these error messages, these type mismatch error messages are so annoying because they don't explain why they're supposed to have this type. Like F. Like maybe it's confused about that. A prime, P A prime. I mean, I guess I should probably call it n prime, huh? But like this is where you have to like start ascribing types. But like the types in this case are like fun f, right? It's just from fin n, right? The problem is that fin cons, right? This is supposed to output as something of type f, right? Okay, let's just come on. why is my editor doing this to me? Undo. Copy. Put it in parentheses. This should be of type f. Type mismatch. Okay, so like let's just go through. A is of type f. Cons. I know it's because I don't have the at. It's because I don't have the at out front. It needs to tell you, this is the exact, oh my God, this is the exact thing that I was complaining about before. It's that like when it gives you the error message, it should tell you like which argument is which, and it should explain that you have like which arguments are explicit and which arguments are implicit. I mean, and it's all to say like, why doesn't it work to simply do this? Because this is the exact thing that I was complaining about to myself before. I feel like this is like super common like bug for me, and somehow I cannot get it through my head. It's just that like when I like see that there's a type mismatch, right? I understand that like somehow it's not telling me like it's telling me that I don't have the right types, but I don't know why. Like, how am I supposed to realize that the problem is that I'm missing this when it's just like assigning totally random type to this? It's like, I see that it's assigning the type of a different argument to the type of one of the arguments, but it's not quite right. It's just like it's not obvious why it would be doing that, right? Because the like okay, wait, I just want to like go to that like whole like blog post I wrote and like check if it was actually literally exactly the missing at. Was it? Let me like find that. Project ideas. Right, because see here, it wasn't. Problem. Now I have to read all this. The problem essential boils down to the fact that G is in the definition has not been cast the field element and it needs to be. Yeah, see, in this case, it was like some like casting problem. Lean complains that it doesn't know how to derive that this is a semi-ring. This is already confusing for two reasons. It's not clear where in the definition that comes up, and G is technically not of type G, but of type Coe sort G, which seems to be represented as that. It's not clear why we need to derive semi-ring. Second error is also confusing. It claims that vanishing poly G is expected to have a type, but doesn't explain why it's expected to have this type. The reason is that because G is of type G, the eval function infers that it is working on a polynomial over G, decides that vanishing poly G should be a polynomial over G. It is only once we realize that we see that both errors have the same root cause. We need to derive semi-ring on G because we are supposed to take a polynomial over it, and types we mismatch the type because it's not a polynomial over G but over K. Yeah, so this was like the fact that this is like a different problem with the exact same presentation, right? The exact same presentation, which is like you get an error and it tells you you have a type mismatch. But so it's like but like for an entirely different cause. Like in this case, the cause was just that I didn't have an at. And in this other case, the cause was that I was like passing it, I was not coercing it before I passed it into some function. But like it was impossible for me to like it's impossible for me to tell like which is which. So there needs to be something changed about the error messaging in Lean to like be like when I have a type mismatch, tell me why. Like tell me how you're deriving the type. Anyway, like it would have totally been solved. Like my suggestion was that like when I get a type mismatch, it should say the type mismatch is because the first such like implicit argument or explicit argument has been referred. It's like I even say here that it should tell you what like the type of the argument is. It should tell you like it should start to make clear what arguments are implicit and what are explicit so that you can be like made aware of what's going on. Okay, all of my ideas are great, and the people in the math-like community should adopt them all. Okay, so like moving on, why does this like, can Simp please solve this? Unsolved goals. Suggest. Okay, so now if I run apply question mark, it will not give me a bunch of random stuff about Vinset because Vinset has been removed. Didn't find any relevant lemmas. I feel confident this is true. If I use this, can I use this for what I'm accomplishing down here? Like apply Finalimsuck. Fail to unify S with this. The problem is that it's, yes, okay, I see why, but the issue is not like a big problem. The issue is that like the order of operations on which mem is applied, right? So S is of type something to prop. Start doing like A, B. B1, AJP2, and prime. Can I just like application type mismatch? Right. I mean, the key problem. Okay, let's act. Okay, so let's like remember to put the add in. And okay, so obviously it's going to be n, and then like what we want is, I think that this like mems, I think that this is like valid notation, right? Oh, it's so annoying to get the type mismatch. Okay, it's because I need F as well. Proved anything yet? My boss tells me I don't have to prove myself. Okay, maybe joke's on me. I have not proved anything yet, but I'm getting very close. No goals to be solved. Okay, great. So that is that. Okay, so that, yeah. Yeah, all of that was just for like the second half of the second half. Yeah, quite a few. How many lines of codes are we at this point? Like 400 or so. It's okay though. There's a lot of like random commented out code. The key is to like it's easy to write a proof in many lines, but it's hard to write it in few lines. Yeah, I should split it in method. It's true. I should like what I should be doing. There's a lot of like things in here that really should all be factored out. Yeah, like VS Code, like I've seen this in other languages where you can do like refactor, and you can like select a portion and then like do refactor, right? I think it doesn't do anything here. No refactoring is available. See, but what should be possible is that you should be able to like, yeah, you can do these refactors. What should be possible is like because like in this language it's, oh, JetBrains. VS Code is trash. Well, of course, like this language only has like VS Code is the only way that I'm able to get um, this like nice readout of the proof. Um, but yeah, you should be able to like refactor things. Okay, where are we? Extract variable. Yeah, all of these things. All right. So this was like the second half of the second half, but I skipped the first half. So all I need to do, like, what else do we have? Okay, we have this sorry at the very end, which is sort of minor. But like this like of the big two parts, this is like the second of those. In the second half, we need to do this. Am I doomed to be a teacher with a PhD? Yeah, quite possibly. Okay, yeah, so this is, okay, yeah, this is where we're at now. Now we have to do all this like sum work. So we have a finset sum, we have a sum over ones. Okay, so this is the interesting thing. Like we did card equals sum ones, then we did this, and now I think we want to undo this. Let's see if this works. Or if it'll be like rewriting under binders. Get wrecked. Yeah, did not find an instance. I bet if I do like simp rewrite though. Yeah, teachers make less than you, but they teach you all your skills. Yeah. Those who can't do teach. That's what they say. All right. The simp rewrite was, of course, successful. Now I just have to figure out what's going on. So I'm doing a sum over this filtered set of fin n to f. Right, so the point is that, right, here's the point. The thing that I have highlighted here is a set of cardinality at most finset.card s to the n, which is very nice because finset.card s to the n appears here. Or maybe I should say like, sorry, finset.filter this function, finset.py finset this. Yeah, okay, so in fact it's exactly that. So if I take this is a set of size finset.card s to the n. And the point is that if we filter out all of the ones that don't work here, then this quantity, for all the ones that, like after we have filtered those ones out, then this quantity should always be at most this, polynomial.nat degree of fin subsequent fnp. Okay, so we're pretty close here. What we've got to do is what we need is some sort of thing to reason about. Okay, let me like switch over to my documentation window on the on like the sum stuff. Point is that a sum, right? This is a sum, and a sum is less than or equal to a product. Yeah, a sum is less than or equal to a product if like the number of things you're summing is less than the first thing, and the size of the things you're summing is always less than the thing. So I bet there's something like finset sum leprod. Ooh, we have immediately gone into the part of the documentation where nothing exists. Maybe the point is that we like build it up out of smaller things, like some less than some, right? The point is that yes, for all I in S, f of I is less than g of I, and what we're going to replace it with is like this is fun S from FinSet cup filter on F to this, and what we are going to replace it with, yeah. So we're going to rewrite that, or we're going to apply transitivity, yeah. In particular, with the function g being the constant function that returns this quantity. This is a little mysterious. Why is it's written as I here, but it's written as polynomial not degree this here. Okay, this makes me a little nervous. Let me just polynomial dot not degree of I is polynomial dot not degree of p prime. P prime is polynomial fin subgroup of fnp. So this whole expression is just I. I don't really get why it's written this way though. At what point did it cease to be written as I? Wait, what? Did it rewrite twice? Did the simp rewrite thing rewrite twice? Why does going from here to here make this rewrite from I to the thing it is now, right? So like here it's just I, but after this rewrite it's this. That's really weird. I guess it is not really critical. Okay, maybe we should just ignore it for now and proceed to do FinSet sum. So transitivity. Well, I don't know if like what I really want to do is apply. I mean, what I really should do is like a calc block, maybe. Transitivity of the less than or equal relation for the argument FinSet dot sum only sum. Can I do just like a G is equal to fun fine? See what this does. As type this implies, okay, well, I'm quite happy to put a variable there for h. We will prove later that this thing is less than what I'm claiming. focus on this goal. Okay, this now feels like a simplification. Because it's a sum. Okay, but it's obviously simplified away way too many things. All these weird polynomial lemmas again. Yeah, really just want finset.sumConst. S small equals mul. That's interesting. Just like where hold up quickly and like, is it because like we don't know that the contents of the like sum are actually like a natural? Yeah, so let's keep that that rewrite it, and we also want to do like a mulcom rewrite. So now we have I times something is less than or equal to I times something, and we can like oh, this is something I was using down here in this big calc block. Mul and mul, mat, apply mat, not done mul and mul, right? Now I just have to like prove this. Ooh, maybe mul and mul left. Yes, should be mul and mul left. All right, seems pleased with that. Right, the other part is yet to be proved. And so card filter is less than the card of the not filter. Okay, I'm gonna take a quick break. I'll be back in a moment. Okay. I guess it's picking up my computer mic now because my other mic was dying. Let me just, yeah, seems to work. Okay, getting close.
the heck? Oh, it was sitting on my what? What's going on? Stop. Yes. Yeah. Okay, so now the fin set, the card. I think the point is that the card filter less than the thing, right? Because this is just the type pi fin set. Yeah. So I bet there's a lemma. Apply LE trans. I bet it's called like finset dot card filter LE. Let's just do like a quick search. Card filter LE. Yeah. Got it exactly right, I think. Okay, but there's some arguments that I have to pass in. Like, I mean, so clearly, I'm a little confused. Can you not just infer them? Maybe I have to put that there so that it knows to like try to infer them. Yeah. Okay, cool. So this should be LE of eq. Because in fact these two things are equal. Does there happen to be a, I wonder if there's like card pi fin set. Seems like there should be card pi fin set. Card pi fin set. Type dot card pi fin set. Card. Yeah, okay, sure. And it's a simp theorem. I wonder if I could just simp. Because it's the constant function, right? It's a constant function. So it's just going to be a product, no goals. Let's just do a little question mark here to make it nice. Cool. Cool, that gets that. So the other part of this is what goes here. Ooh, looks like we have a nice intro. E and HP. All right, so B is in this filter, and the point is that we can simplify that to I, right? And this, yes, this is where the thing that I had before, this is where all the way up here, polynomial.card roots is going to come in handy. So this is finset.card, finset.filter, and this. Simp. Like at the very least, we should be able to get I on the right-hand side. Right, of course it's I, but and this, like, it's looking even even more like what the what probably polynomial card roots outputs. Let's take a look. Polynomial card roots. Is there like a nat degree version? Yes, there is. Seems good to me. Let's apply it. Okay, but the like final issue, is it well understood that this polynomial that I have here is the polynomial that I want? Also, it's talking about finset.card. Multiset.card. Finset is less than the multiset. Okay, so seems like what actually has to happen is maybe something like apply transitivity trans of this and polynomial dot card roots prime taking a while to load again. A real while to load. Unknown constant polynomial dot card roots prime. Okay. Cool. See what it thinks of that. Yes, it's a theorem about a multiset, so we're at some point have to like gonna talk about how a finset has less roots than a multiset. I wonder if there's some like multiset version of Schwartz-Zippel. It's interesting. Still complaining, I see. Apply tactic failed. Failed to unify something less than a polynomial nat degree something with something that looks exactly like that. That's a bit annoying. Failed to unify. Tactic apply failed. Failed to unify something is less than a polynomial dot nat degree. Okay, maybe if I provide the polynomial. I mean, the polynomial is this. Of course, p prime, right? This can be more succinctly written as p prime. Okay, now you're complaining about this. Type mismatch. Argument has type this. But argument is the type of a function. Card roots. Argument. Net degree of this. Right. Multivariable polynomial Finn-Sokogwev. This is a dot coef maybe? No, this is not what I want. Is it what I want? What is that? Okay, multivariable polynomial Finn-Sokogwev Fn is an equivalence, like too fun. It's an equivalence between multivariable polynomials and polynomials of multivariable polynomials. So I get a polynomial of multivariable polynomials. So when I apply it to P, I get a polynomial of multivariable polynomials, do I not? P prime. I feel like I should just write P prime. Can I not? You know, just like P prime, dude. That's what I'm looking at. Ooh, it's a diamond. That's not good. Has type polynomial, MV polynomial, com semiring to semiring, but is expected to have type. Okay, like MV polynomial com semiring, but is expected to have type com ring to com semiring. Oh boy. Oh no, this is not good. This is something that I don't know how to deal with necessarily. The problem is that it doesn't, it's like inferring the wrong type. Oof. Not good, not good. Yes. I should have like suspected that this is going to happen when it like said I cannot match these types, and it was like exactly correct. I'm just like trying to think of how do I even make a minimum working error out of this? properties can be used when generating simple functions combined with. Right. What is this? Oh. Is it suggesting that I don't like using too many parentheses? Yeah. Let me try and like understand. So MV polynomial, it's all within these last things. MV polynomial fin NF is a con semi-ring. Yes. Schwartz-Zippel only applies over fields, right? That's weird. Where do you divide? Where do you need division? In this proof. I guess it's a property of like. No, it's not a property of card roots. I don't really get that. Okay, maybe this is something to like come back to. Diamond. Sorry. Yeah, it takes a while. Okay, but we're very close to done. There's some like. Okay. Yeah, apply did not find any relevant. I'm just like very. Like this seems like something that's worth like posting to the like forum maybe. This fin lemma. Right, I just have right a fin n+1, and I want to show that if I have a tuple, right, some property is true of all elements of the tuple if it's true of the head of the tuple and of the tail of the tuple. Okay, so that seems like neutral. I wonder if like SIP would solve this. Mem.py fin set. What? It seems like we're close to seems like this is like yet another instance of the same like lemma requirement. Right? Wait, like what did I just do? Look. Undo. Sorry, I didn't. The thing is, like this, right? Okay. I ran simp. And it told me this. Fin typed up in my business. Okay, okay. So clearly, this lemma already exists in the library. fin type mempy fin set. Fin type mempy fin set. Yeah, okay. So this is fin mempy fin set. It's just fin type dot mempy fin set. Just like make sure that everywhere in the library should be fin type dot mempy fin set, fin type dot mempy fin set. It's just the exact same, right? Should be fin type dot. Cool. Seems like we eliminated that. Okay. For all cons in S, if and only if. Yeah, this is like startlingly similar to what I feel like I was doing. It's like I was here. Fin cons mempy fin set. Cons mempy fin set. It's just interesting that like, what am I reading here? Fin cons, right? Takes in 3 arguments. I've only provided 2 here, of course. Cons mempy fin set F. Right. It is an element of the set of functions. Okay. And if I scroll back down here, I have fin cons. Fin cons of this is in S. So I feel like it's almost the case that what I want to do is like it's not just true that this is this, but it's true all the time. Like for all A1, fin cons this is in S. For all A1, F in S, F of A1 is in S. This is equivalent. What did I just delete? Mempy fin set? Fin type dot mempy fin set. Of course, this is the second one. It's a simple lemma, but I want to rewrite it backwards. Like down here, like right here, I want to write fin type dot mem pi fin set fin set. Right. The problem is it's not going to be simp normal form or something. What happens if I just like simp here? That's HAB1 and HAB2. Now these can all be commented out. I mean, it's interesting. Cutting away even more, we can do this with like Tato or something. Okay, but we don't want fin type mem pi fin set, and we don't want all this random polynomial. Yeah, I feel like because I'm reversing a simp lemma, this is not the kind of thing that is approved of, like Tato. Tato didn't work. That's interesting. But surely this is fine. Yeah, interesting. I don't get it. Weird. Yes, it all leaves behind this problem of like neither this theorem nor this theorem has a proof. It's like I do this simplification first. Oof. It's like I want it to be a little bit more general than this. Like it's like more general than this and this, right? Because this one has the like element of S property, and this one, you know, abstracts that to a proposition, but it's not if and only if, like this one is. Like cons, all, like for all cons. Like the lemma should be something like lemma for all eval con. Cons eval. I don't know what it should be called. The point is that, like, if I copy all of this, NSAB, I think the point is that, like, the property is true of, like, for all n prime in fin n plus 1, S is true of this if and only if this is true and SA. Probably it should be permuted. We can delete all those. Why is it suggesting this? Does sim only do anything? Not doing anything, right? Yeah. So a lim suck would be like one consequence of this. It's like one direction of it. Rewrite for all eval. Pattern is a Merriweather. Simple, can I do this? Okay, it's fine with that. What's going on? For all cons eval. Yeah, a lot going on here. Well, I've been going for a while. Maybe I should turn off now.